and a distinct conjugate, q prime, are both root of a given quaternion polynomial, then in fact the entire sphere is a root, which is interesting. So this means the characteristic polynomial is a factor of p of x. Applications of Niven's algorithm. In general, if the trace, as we said, trace and norm of a root of p of x are known, then you divide it by the characteristic polynomial. Then either we have f is 0, which means g is 0. Thus, we can either determine that its characteristic polynomial is a factor, or we can determine a linear equation which gives a root. In the latter case, f is not 0, and it is easy to conclude that these two equations are satisfied. And you may say, well, how do I know? Find the root. Whose root? How do I find the norm and trace of a root that I don't know? And indeed, that's not easy to determine. What Niven showed is that the reverse is also true. That is, if we consider an equation, these two equations that as equations in T and nu, then any solution gives a trace and norm of a 0, and therefore we can do the division, either get a factor or a 0. But as noted by Niven himself, this approach is impractical because it requires a simultaneous solution of two equations of degree 2n minus 1. The factor theorem is a key result on polynomials over the division ring, which can be proved in a straightforward fashion. This proof can be found in this book, Lamb. I must say that when I saw a proof of the Fundamental Theorem of Algebra given by Niven or others who followed it, I didn't like their proofs. And I felt that they could prove it in a more constructive way, and I'll show that, what I mean by that. Anyway, the factor theorem says that q is a root if and only if x minus q is a factor, just like the usual complex numbers. And the second part is a very interesting part, and says that if you have a polynomial that factors as a product of two polynomials, if you take a particular value q, suppose that h of q is not 0, then p of q is, you see, we cannot just plug in q in here. We have to do this business. Okay, so in particular, if q is a root of p of x and h of q is not 0, then aq A inverse is a root of q of x. Classification of zeros of a quaternion polynomial. Here is one way that one can define the roots. We say a root is of multiplicity k, just like the complex case, if x it factors into q of x times x minus k, and a simple root if k is equal to 1. We say it's an isolated root if there is no roots, any other roots in its neighborhood, in a neighborhood of p of x, neighborhood of the root. We say it's a spherical root if the conjugacy class is contained in the zeros of the polynomial. And we call q a sphere of zeros of p of x. We say it's a distinguished spherical root if q is a spherical zero of p of x, but q has no distinct conjugate as a root with the same multiplicity. I'll tell you what I mean by this. So an isolated root may have multiplicity larger than 1. As an example of a distinguished root, here you see that I is a root, and it is the entire sphere is a root because of x squared plus 1, but I is also another root which has multiplicity 2 here. for this polynomial, but no other conjugate has it. Each sphere of zeros of a quaternion polynomial can contain at most one spherical root of higher multiplicity than its distinct conjugates. Structure of zeros, this theorem, structural theorem, was proved by, I'm not sure how to pronounce it, Paguri and Shapiro in 2004. It really follows trivially as a consequence of the factor theorem and the fact that if Q and a distinct conjugate are both roots of P of X, then so is the entire conjugacy class. The theorem says that suppose we take a quaternion polynomial of degree n, then the number of isolated zeros plus twice the number of sphere of zeros counted with multiplicity is at most n. We can use the factor theorem to argue that this quadratic equation has only one simple root, namely j. Okay, let me skip that part. Solving a quadratic equation. I mean, you take a look at a simple quadratic equation and you want to solve it over the quaternions. What do? It's not so easy. In fact, I discovered an article which is dedicated entirely to considering different cases of B and C and giving a solution to that. It's much tougher cases of a quadratic equation are this, where x does not commute and you want to find a solution to this. I will give a simple solution to that in a way trivializes their solution. Here is what I call a constructive proof of the Quaternion FTA. A logician may object to that and by saying, what do you mean by constructive? But here you see what I'm saying, what I mean. You take a quaternion polynomial, let's define its conjugate, where we, as in complex case, we conjugate the coefficients, and take this polynomial, P of x times P bar of x. If you look at Niven's paper proving the fundamental theorem of algebra, he takes a similar function, but he takes P bar of x times P of x. And that makes it more difficult to see the proof of the fundamental theorem of algebra, in my opinion. But it happens to be the same as this function. So this is like taking a polynomial and multiplying by its conjugate in the complex case. Then f of x has real coefficients. That's one simple property. If theta is a complex number that is a root of f of x, then P of x has a root in the conjugacy class of theta. Furthermore, if Q is a quaternion and a root of P of x, then there exists a complex number, theta, which is in the conjugacy class of Q, that is the root of f of x. More precisely, here is really the story, simple proof of the fundamental theorem of algebra for quaternion polynomials. Suppose theta is a root of f of x. Then, if theta is not a root of its conjugate, then this number is a root of P of x. Suppose theta is a root of f of x. If theta is a root of P bar of x, and theta bar is not a root of P bar of x, then this is a root of P of x. And if theta is a root of f of x, suppose it's a root, and suppose that both theta and its conjugate are roots of the conjugate polynomial, then both theta and theta bar are also roots of P of x. In particular, if theta is real, then P of theta is equal to 0. Suppose that Q is a root of P of x, then theta, the complex conjugate sort of it, is the root of f of x. So what this says translates into, in a simple way, is that if I have a quadratic equation and I want to solve it over the quaternions, I form the quartic equation and then I solve it. I know there is a closed formula for those. Here is a question which I do not know the answer to. If I give you a cubic quaternion polynomial, can you solve it? Like in the case of cubic polynomials over the complex. Is it solvable? I don't know the answer to that. Maybe I don't know algebra, enough algebra. An example of computation, application of this theorem is computing the nth roots of a quaternion. And if you look in the literature, there are several articles actually on this subject, including by Niven himself. And the theorem which I mentioned simplifies computation of nth root of a quaternion. You just look at this polynomial. It's a real polynomial of degree 2n. And two cases you need to look at. If q is real, then f of x is that polynomial. Its roots are the nth complex root of q. However, since p of x and p bar of x are identical, for n bigger than or equal to 3, the complex roots of f of x come in conjugate pairs. And our theorem implies the roots of p of x also come in conjugate pairs. Thus, there are infinitely many roots to p of x. In this case, one can obtain an exact factorization for p of x. Let me go over this quickly. Anyway, this theorem turns a nth root computation, trivializes that too. Because you just go to this real, you find its roots, and you solve, then you apply this theorem. If q is not in quaternion, which is not a real, then the roots are the complex nth roots of theta and the complex nth roots of theta bar. Okay. Factorization of a polynomial. Incidentally, what this theorem also shows is that in order to compute the roots of a quaternion polynomial, we can simply apply any complex polynomial root finding to this function f of x, because by this conjugation we can recover the roots of p. So I will talk about that later too. So when you take a monic polynomial of degree n, then we know it factors completely into linear terms. But of course, it doesn't mean that all the qi's are zeros of that polynomial. And its conjugate also factors in the reverse order. And the function f of x turns out to be the product of quadratic terms, which are either characteristic polynomials or of the form just a quadratic of the type x minus qi squared. Factorization and zeros. Here is a theorem that says if you have a factorization like this, then we know p of x has a root in the conjugacy class of each quarter. That's the best that they claim in this theorem. And in fact, we can give a more precise version of that. If we have a set of quaternions qi, and f of x, p of x factors into that, then we simply look at the complex numbers, theta I, the complex conjugate of qi's, and either this is a root or this is a root of p of x. So we have two cases. Rather than saying that there is something in this conjugacy class, we can just say either this or that. Approximation of zeros of a quaternion